systems that built the foundation of modern engineering. Let us begin. The primary element that enabled the urban expansion of the Roman Empire was the system of aqueducts, which allowed water to be transported to the city over long distances. The most fundamental parameter required for these systems to function is the gravitational gradient. For a water channel to maintain a continuous flow over kilometers, it needed an average slope of 30 centimeters for every 100 meters. This gradient was calculated using a 6-meter-long wooden measuring instrument called a caravans, which contained a water level. If the slope were too steep, the velocity of the water would erode the inner surface of the channel. If it were too low, the water would stagnate, leading to sediment accumulation. This delicate balance was a most fundamental static calculation of Roman engineering. The selection of materials used in the construction of watercourses is directly related to the chemical composition of the water. The interiors of the channels were lined with a waterproof mortar called opus signatum, consisting of lime, sand, and finely ground terracotta fragments. This mortar possessed a structure that hardened further over time upon contact with water, preventing leakages. The reason for constructing closed channels was to prevent algae growth by cutting off the water's contact with sunlight and to minimize the rate of evaporation. However, even in these closed systems, the calcium carbonate within the water formed a lime crust, sinter, on the inner surfaces of the channels over time, a technical problem that reduced the discharge rate. Maintenance crews had to periodically enter these channels and mechanically scrape away the hardened lime layer. The massive arch structures, built when water had to cross valleys, were not merely aesthetic, but a result of absolute static necessity. If a valley was too deep and the height of the arches exceeded 50 meters, engineers preferred the inverse siphon system. In this system, the water was taken in lead pipes, released rapidly down one side of the valley, and driven by the resulting hydraulic pressure up to a lower-level reservoir, castellum, on the opposite slope. For the lead pipes to withstand this high pressure, the pipe wall thickness and the soldering techniques of the joints were extremely critical. The internal diameter of the pipes was determined mathematically to balance the frictional resistance, hydraulic loss, of the water. Upon reaching the city center, the water entered main distribution towers called castellum aquae. Here, the velocity of the water was reduced and sediments were allowed to settle at the bottom. Distribution was divided into 3 different priority groups. The first group comprised public street fountains used free of charge. The second, imperial baths and social facilities. And the third, private lines leading to the residences of the wealthy. For every residence receiving water from private lines, a standard bronze nozzle called a calyx was installed. The diameter of this nozzle served as a flow restrictor determined by the tax bracket the subscriber paid. The seal on the nozzle was regularly inspected by state auditors, curator aquarum, to prevent water theft and the installation of illegal lines. The sewage systems of ancient Rome, such as the Cloaca Maxima, performed a hydraulic discharge function as vital as the entry of clean water into the city. These massive tunnels beneath the city had a specific hydraulic gradient to carry rainwater and waste to the Tiber River. The circular vaults in the ceiling sections of the tunnels were designed to distribute the urban load above onto the side walls. This system also provided drainage for the city's groundwater, serving as a passive ground improvement method that prevented building foundations from softening and collapsing. This hidden and monotonous infrastructure of Roman engineering is the greatest technological achievement that allowed the city to grow at the same geographical point for 1,000 years. The layered structure and soil mechanics of ancient Roman roads represent the most static yet vital engineering field that ensured the empire's logistical continuity. A Roman road was not merely a stone pavement, but a complex structure consisting of four distinct engineering layers. At the lowest level lay the statumen, a layer approximately 30 centimeters thick, composed of large, coarse stone blocks. The function of this layer was to distribute the superimposed load evenly onto the natural soil and to prevent the road from sinking in marshy or soft terrains. Above the statumen, a 20-centimeter filling layer called rudus, consisting of a mixture of broken stones and lime, was spread. This layer provided elasticity to the road and acted as a cushion to absorb vibrations. On top of the rudus, a mixture of fine gravel, sand, and lime powder known as nucleus was poured. This mixture was compacted with massive rollers to form a completely impermeable, hard surface. The uppermost layer of the road, the pavimentum, consisted of basalt or volcanic stones, polygonal blocks, carved to fit together perfectly. The angle at which these stones were placed was adjusted to create a slight curve, camber, in the center of the road. The purpose of this curvature was to prevent rainwater from accumulating in the center, allowing gravity to direct the water toward the drainage ditches, fossae, on either side. Since the seepage of water into the road body would cause the lower layers to expand during freeze-thaw cycles and displace the stones above, this drainage system was a technical necessity that extended the road's lifespan for centuries. The total depth of a Roman road could sometimes reach 1.5 meters, which exceeds even modern highway standards. The volcanic chemistry of Roman concrete, opus cementitium, is a molecular marvel that has allowed these structures to remain intact for thousands of years, even underwater. When slaking lime, Roman engineers added volcanic ash from the Pozzuoli region near Naples to the mixture. This ash was extremely rich in reactive silica and alumina. When mixed with lime and water, these substances entered a chemical reaction to form calcium-aluminum silicate hydrate structures. These crystals filled microcracks within the concrete over time, providing the structure with a self-healing property. Especially in maritime harbors, magnesium and sodium ions in seawater interacted with the volcanic minerals in the concrete, imparting extra hardness to the structure. In contrast to modern concrete, which corrodes and disintegrates in seawater, Roman concrete increased its mechanical resistance upon contact with water. The heat transfer mechanism of the bakeries in ancient Pompeii is one of the most monotonous yet efficient examples of thermodynamic principles used in commercial production. These ovens were massive circular structures typically built from volcanic basalt stone. The wood fire, the source of heat, was not lit in a compartment beneath the oven, but directly inside the baking area. The heat capacity of the stones was so high that once the oven reached its target temperature, the stones could radiate heat back at a constant degree for hours, even if the fire was extinguished. The dome structure of the oven allowed the heated air to create a circular flow, convection, inside, thereby guaranteeing that every surface of the bread was baked evenly. The order in which dough was placed in the oven was determined by the thermal gradient at that moment. Hard-crusted breads requiring the highest temperature were baked first, while thin products requiring lower heat were baked in the final stage. The hydraulic bellows systems used in Roman metallurgical workshops were another mechanical element that increased the efficiency of smelting furnaces. The circular motion obtained from water wheels was used via eccentric shafts to open and close massive leather bellows. This system increased the amount of oxygen entering the furnace threefold compared to manual bellows, making it possible to reach temperatures closer to the melting point of iron, approximately 1538 degrees Celsius. High temperatures allowed for a more efficient separation of slag, impurities, from the metal, which increased the tensile strength of the manufactured swords, armor, or construction clamps. The production standards in these foundries constituted the actual technical engine behind the military and architectural power of the empire. The logistical design and moisture control mechanisms of Roman granaries, or horea, represent the most static yet critical engineering field, ensuring the empire's food security. These massive warehouses were not merely storage spaces, but technical structures equipped with passive climate control systems to prevent grain spoilage. Since a moisture content above 14% leads to fungal growth and insect infestation, Roman engineers utilized the suspensura system, an elevated flooring method. The floor was constructed atop small brick pillars, pilae, raising it approximately 50 centimeters above the natural ground. This allowed for a continuous airflow beneath the floor, preventing moisture from seeping upward and guaranteeing that the grain remained dry. Narrow-angled ventilation slits in the exterior walls were positioned to optimize cross-ventilation, convection, while preventing rainwater from entering the interior. The mechanical advantage calculations of ancient cranes, specifically the trispastos and pentaspastos mechanisms, formed the basis of heavy load management at Roman construction sites. A trispastos, or three-pulley crane system, could theoretically triple the applied force. However, the greatest technical obstacle in these systems was frictional loss. To reduce friction of the ropes against the pulley grooves, animal fats were regularly used as tensile strength of the rope was calculated based on the braiding density of the hemp fibers. For heavier blocks, polyspastos cranes utilized massive human-powered drums, tread wheels. The weight of a person inside the drum, combined with the advantage of the torque arm, allowed for the placement of multi-ton marble columns with millimetric precision. The wear allowance in the bronze-cast axle bearings of the pulleys was a technical parameter constantly monitored for construction speed and safety. Water drainage systems in Roman mines were a hydraulic limit that determined the depth of underground operations. In deep mines such as Rio Tinto in Spain, massive noria water wheels arranged in series were used to evacuate groundwater. These wheels, rather than utilizing the energy of flowing water, were turned by human power to lift water incrementally to the next level. In systems where up to 16 wheels operated in sequence, water could be discharged to the surface from depths of hundreds of meters. The water tightness of the wooden paddles was maintained with a mixture of hot pitch and lime, while the frictional heat in the axle bearings was cooled with water. This mechanical continuity had to be maintained 24 hours a day in shifts for the mine to remain operational. A single hour of interruption in the pumping system could result in the flooding of the galleries and the loss of all capital. The combination of these monotonous techniques constitutes the invisible engines that created the Roman world's famous perception of stability and durability. Every screw thread, every mortar mix, and every degree of gradient is a piece of the empire's thousand-year static balance. The standardization of units of measurement and calibration methods in the ancient world is the most static technical subject that formed the legal foundation of trade and engineering. The unit of length known in Rome as the pes, foot, corresponded to approximately 29.6 centimeters. However, to ensure this measure remained consistent across every province, the master bronze standard kept in the capital was taken as the reference. Copies sent to the provinces were cast from hard bronze with a low coefficient of thermal expansion and were stamped with the imperial seal. The calibration of measuring instruments, particularly the groma used to determine land boundaries, was performed by vertically aligning lead plumb bobs to minimize wind interference. The stretch in the plumb line was fixed by saturating the linen thread with beeswax. This technical stability was a bureaucratic precision that kept the margin of error near zero for every mile, millipassus, of the thousands of kilometers of imperial roads. The amphora standards used in liquid and dry volume measurements determine the unit volume-to-weight ratio in the calculation of logistical costs. A standard Dressel 1 type amphora had a capacity of approximately 26 liters. The volumetric calibration of these vessels was verified by weighing the amphora after it was tared and then filled with water at a specific temperature. The conical base structure of the amphora not only facilitated stacking in ship holds but also allowed the sediment of the liquid to collect in a narrow area, reducing error in net volume calculations. Customs officers at ports would inspect the weight, quality, and tax status of the goods via the tituli picti, painted inscriptions, on the exterior surfaces of the amphorae. This data was matched with the records in Rome's tabularium, state archives, allowing the empire's total food supply to be mathematically monitored. The precision of mechanical scales and weight sets is another element that ensured the legal security of trade. The steel yard or equipondium system used in Roman scales relied on the millimetric precision of the notches carved into the lever arm. Each notch on the bronze arm represented the torque differential created by the displacement of the center of gravity. The precision of scales used in goldsmithing approached modern-day milligram levels, and the pans of these scales were kept in enclosed compartments to prevent interference from air currents. Stone or bronze weights used in weighing operations were selected from high-density materials to be resistant to wear, and their value inscriptions were etched using deep engraving methods. This system is a technical language that ensured the same mathematical tongue was spoken in every marketplace from Alexandria to London. The measurement and control of the coefficient of thermal expansion in glass were of vital importance, especially in the production of ancient laboratory and pharmaceutical equipment. To prevent glass vessels storing medicines from cracking due to chemical reactions or temperature fluctuations, the ratio of minerals such as borax added to the glass batch was meticulously adjusted. The wall thickness of these vessels was determined by the continuity of the glass blower's breath pressure during the blowing process. A 1 millimeter deviation in wall thickness could cause thermal stress to accumulate at a single point during heating, leading to the vessel's explosion. Therefore, after technical glassware was produced, it was subjected to a gradual annealing process within a kiln and then inspected by holding it to the light to check for internal optical refractions, stress lines. This quality control process was a silent standard forming the technical infrastructure of ancient medicine and alchemy. In conclusion, whether it be the logistical calculations of caravans on the Silk Road or the degrees of gradient in the aqueducts of Rome, history shows that power does not reside solely in heroes, but in these monotonous technical details. The engineering principles that form the foundation of the modern world today were built with the methodical patience of these nameless engineers who decoded the language of stone, water, and metal thousands of years ago. As time flows on, these structures and systems continue to carry that heavy and static knowledge of the past into the future. The methods and documentation standards of the ancient world, specifically the standardization of script characters on papyrus and parchment, represent another static technical element that ensured information was transported across thousands of kilometers without degradation. In massive knowledge repositories like the Library of Alexandria, a method called stichometry was employed to minimize the margin of error during the copying of texts. This method relied on calculating the total line count of a text and noting this figure at the end of each page. If a scribe omitted a line, the total count at the bottom would not match, allowing for immediate error detection. The viscosity of writing inks was adjusted according to the acidity of the mixture of oak galls and iron sulfate, thereby preventing bleeding, ink vomiting, where ink spreads excessively between fibers. This institutional rigor was the technical guarantee that commercial contracts and engineering plans maintain their legal validity over centuries. Lighthouse and optical signaling systems used in maritime navigation are another low-frequency engineering field, ensuring the nocturnal safety of sea trade routes. In massive structures like the Lighthouse of Alexandria, the focal length of the colossal bronze mirrors was mathematically calculated to ensure the light was visible on the horizon from approximately 50 kilometers away. The combustion rate of the resinous woods used as a light source and the density of the smoke produced were constantly monitored by lighthouse keepers. Aerodynamic air ducts were situated at the upper sections of lighthouse towers to prevent wind from scattering the smoke. This system was not merely a light source, but a carrier of a coded optical language that signaled shallows and harbor entrances to ships. The fact that each harbor possessed its own unique light rhythm, or mirror angle, functioned as a primitive GPS system, allowing sailors to determine their coordinate-based position in pitch darkness. Finally, the coinage minting techniques and metallurgical purity audits of the ancient world formed the molecular-level trust of the global economy. The hardness of the steel dies used during the striking of a coin was increased through carburization, ensuring the sharpness of the details on the coin even after thousands of strikes. The serrated edges or specific markings on the coin were mechanical security measures developed to prevent clipping, a fraudulent practice aimed at stealing precious metal from the edges of the money. Assay controllers in the mints tested the purity of the molten silver using a method called cupellation. In this process, silver mixed with lead was heated in crucibles made of bone ash, and the amount of pure silver remaining was measured as the lead oxidized and was absorbed by the ash. This technical procedure ensured that money was not just a piece of metal, but a mathematically verified unit of value. Within this heavy and methodical flow of time, every technical detail gave birth to the next. Sand, stone, metal, and ink, combined with the discipline of human intelligence, constructed the silent but unshakable backbone of history. The ancient ruins and texts we observe today are, in fact, more than works of art. They are the surviving pages of a millennia-old engineering handbook. For the careful observer, this knowledge, waiting silently, continues to exist with the same stillness and the same precision. Ancient logistical packaging and container sealing technologies were a system equivalent to today's security barcodes, ensuring that goods were transported over thousands of kilometers without spoilage or unauthorized access. The mouths of wine and olive oil amphorae were first closed with a cork stopper or a terracotta disc, then coated with certain harmonics in the actor's voice, compensating for acoustic attenuation in an open-air environment. This represents the quietest and most methodical application of trigonometry and wave physics on buildings. The mechanical torque calculations of ore crushing and grinding machinery used in mining facilities represent the ancient origins of heavy industry. Circular motion derived from water wheels was converted via eccentric shafts and cam systems into the vertical rising and falling of massive stone hammers, stamps. The shape of the cams used in these systems was carved to maximize the hammer's freefall velocity and impact energy. The ore was mixed with water to form a slurry and pulverized to a micron level under these mechanical stamps. In the mercury amalgamation method used for separating gold and silver, the rate at which mercury bonded with the metal, followed by its separation through evaporation, was managed in closed alembics with extremely low temperature increments. Every gram of loss in this process was a technical efficiency parameter, affecting the mine's annual profit and loss statement. Within this heavy and technical flow of time, every page of history consists of a technical drawing, a chemical formula, and a mathematical calculation. Humanity's progress has risen on the shoulders of these monotonous but flawless systems. Rivers flow, wheels turn, stones are carved, and this static knowledge of the past continues to form the silent foundation of today's world. The flow stabilization and mechanical feedback systems of ancient water clocks, clepsydras, represent a high-level field of fluid mechanics aimed at reducing the margin of error in time measurement to mere seconds. Since the rate at which water empties from a vessel depends on the water level height, hydrostatic pressure, simple vessels could not indicate time linearly. To overcome this technical challenge, engineers developed the constant level cistern system. A continuous supply of water was provided to the main reservoir, and excess water was discharged through an overflow pipe, keeping the internal water height millimetrically constant. This ensured that the discharge rate from the bottom outlet remained uniform at all times. A float rising in the receiving vessel would rotate a shaft with carved gear teeth, moving the hand on the dial. In advanced models, conical valves were utilized to adjust the flow rate to compensate for seasonal variations in daylight hours. These devices served as the technical arbiters of ancient bureaucracy and judicial durations. Ballast management and stability calculations in ancient naval engineering were the most static technical elements, minimizing the risk of foundering in offshore transport. An empty ship would rise too high on the surface due to buoyancy, losing its equilibrium. To prevent this, heavy river stones or sandbags, known as ballast, were placed in the lowest part of the ship, bilge. The center of gravity of the ballast had to be positioned directly beneath the ship's geometric center, metacenter. Otherwise, the vessel could list and capsize in heavy seas. As commercial cargo was loaded, the weight and position of every amphora were mathematically calculated to maintain this stability. To prevent bulk cargo, such as grain, from shifting to one side during the voyage, holds were divided with shifting boards. This was a silent logistical engineering feat that maintained the delicate balance of a multi-ton mass upon the water. Alloy segregation and surface enrichment techniques in ancient coinage were metallurgical procedures implemented to maintain the balance between a coin's nominal and metallic value. In the production of silver coins, when low-grade silver alloys were used, e.g. 80% silver, 20% copper, a pickling method was applied to prevent the coin's surface from appearing dull or coppery. Newly minted coins were submerged in organic acid baths to dissolve the copper atoms on the surface. As a result of this process, a microscopic layer consisting solely of pure silver remained on the coin's surface. This technique was a form of surface engineering that ensured the coin's public acceptance. However, over time, this layer would thin due to circulation wear, revealing the base metal underneath. This serves as the most concrete physical evidence used in the analysis of ancient inflation and monetary devaluation. This mechanical progression of human history is hidden in every gear click, every drop of flowing water, and every cooling phase of metal. History is not merely a collection of grand events, but the continuity of these monotonous and flawlessly functioning systems. This technical harmony of stone, metal, and water continues to whisper the static knowledge of the past into the foundations of the modern world. The structural integrity of wooden structures and furniture in the ancient world relied heavily on mechanical joinery techniques due to the corrosion, risks, and costs associated with metal nails. Systems such as the dovetail joint and the mortise and tenon were applied by calculating the natural grain direction and tensile strength of the timber. The surface area at the junction of two wooden components was expanded to distribute the shear force imposed upon it. The hygroscopic nature of wood, its expansion and contraction according to ambient humidity, was a coefficient of change considered in the tolerance margins of these joints. If a tenon were fitted too tightly into its mortise, the swelling of the wood in humid conditions would lead to structural cracking. If fitted too loosely, the connection would fail in arid conditions. Therefore, small wooden wedges, dowels, inserted into the joints served as a flexible fastening mechanism against humidity fluctuations. The chemical composition of ancient glues used to enhance the mechanical resistance of these connections relied on processing animal proteins and vegetable resins at specific temperatures. The most common isinglass, fish glue, was produced by purifying collagen proteins derived from the air bladders of species such as sturgeon. These protein molecules liquefy when heated with water, penetrating the wood fibers and bonding them at a molecular level upon cooling. The drying rate of the glue was directly related to the relative humidity of the environment. Excessive drying speed caused the glue to become brittle, while excessively slow drying could lead to fungal growth. For outdoor structures carrying heavier loads, water-resistant and thermoplastic adhesives made from a mixture of pine resin and beeswax were preferred. The viscosity of these mixtures was regulated through temperature control during application, forming a completely impermeable barrier once solidified. The technologies of marquetry and veneer in ancient carpentry involved the mathematical arrangement of different wood species' physical hardness and color variations. The tooth density of the saws used to cut thin layers of exotic woods, ebony, cedar, rosewood, was determined by the number of teeth per millimeter according to the wood's fiber structure. Ensuring that the expansion coefficients of different wood species were compatible was a critical technical parameter to prevent the veneer from delaminating from the primary substrate over time. The blade angles of the planes used to smooth these surfaces were adjusted as shallow or steep according to the grain direction. In the final stage, natural abrasives such as shark skin or oils mixed with fine sand were used to eliminate surface roughness. This meticulous surface treatment process was a passive protection method that increased the material's resistance to external factors. This microscopic progression of human history is hidden in the interlocking of every wood fiber, the solidification phase of every drop of glue, and the mark left by every sawtooth. History is not merely a sum of great wars, but of this silent and methodical craftsmanship, the effort to understand the language of materials. This technical harmony of wood, stone, and metal continues to whisper the static knowledge of the past into the invisible foundations of the modern world. In Roman and Hellenistic cartography, the process of projecting the spherical structure of the earth onto a flat parchment is a complex data processing sequence that forms the basis of modern projection geometry. Ancient road maps, such as the Tabula Peutingeriana, focused on topological continuity rather than geographical accuracy. In other words, it was not the curvature or incline of a road that mattered technically, but the distance between stops and their logistical connections. Distance data on the map were calibrated based on field data collected by professional survey teams known as mensores using odometers, mechanical systems that dropped a pebble for every rotation of a wheel. During the integration of this data into a central master map, how to compensate for longitudinal deviations caused by the Earth's curvature was the most static yet vital debate in ancient astronomical and trigonometric calculations. The maritime routes marked on these maps were a visualized summary of the text-based technical manuals known as periplus. A periplus text defined distances between ports in units of one-day sail and specified the depth of shallows along the coastline and whether the bottom structure was sandy or rocky for the anchor's grip coefficient. This technical data set formed a navigation algorithm that allowed captains to determine their location in the dark or in fog simply by examining samples taken from the seabed with a sounding lead. The color and size of sand grains adhering to the tallow placed in the hollow of a sounding lead were matched with geological data on the map to determine the ship's coordinates with a manageable margin of error. Imperial tax records and property maps, cadastry, were managed through a land parceling technology called centriation, based on dividing the land into a massive grid system. The stones, termini, defining the boundaries of each parcel, centuria, were aligned on both vertical and horizontal planes, and a copy of these records was engraved onto bronze tablets and archived in local administrative centers. This system ensured that property boundaries were tracked not just by sight, but by mathematical coordinates, minimizing the margin of error in agricultural taxation. The impact of landslope on drainage channels was calculated as a hydraulic variable in these parceling plans. This methodical rigor is the invisible bureaucratic mechanism that allowed a geography of thousands of kilometers to be managed from a single center through paper and ink. Thus, this technical journey, stretching from the logistical depth of the Silk Road to the hydraulic engineering of Rome, and from the molecular structure of metal to the fiber resistance of wood, concludes with a standardized data network that holds all these systems together. History is the sum of these static but flawlessly functioning gears, measuring instruments, and chemical formulas. As rivers continue to flow, roads continue to stretch, and machines continue to turn, this methodical silence of the past will silently carry the foundations of the modern world. Within this heavy and technical flow of time, systems will always continue to work, and data will always continue to be recorded.